Hey, going to start looking at magnetic forces and fields, kind of a natural progression from our last chapter on electrical forces and fields. So these are the outcomes for this lesson. Take some time to have a look at it, freeze the screen if you like. Really comes down to three things, just making sure we all understand the idea of magnets and their kind of two poles, the laws about attraction and repulsion, being able to visualize magnetic fields under different situations, and probably the big one for this lesson is going to be this thing here on the hand rules for determining the direction of magnetic fields. So let's start with the basics. We're all familiar with the idea of magnets and the fact that a magnet, most people think of a bar magnet when they think of a magnet, has its two poles, north and south, and the law of magnetism states that like poles repel and unlike poles attract each other. That means if I put a magnet here with its north pole near the other magnet's north pole, we would expect a repulsive force between these things. Important to note, no matter what happens in terms of the size of one magnet or the other, Newton's third law still rules the day. Whatever the force is on one, it's equal and opposite to the force on the other. So these are mutual forces of attraction or repulsion when it comes to magnets. The other option, I guess, would be if we were to put the south pole of one magnet near the north pole of another one. That's the case where we get attraction between these two things, and again, equal and opposite forces of attraction. So really just those two options when it comes to bar magnets near each other. They'll either attract or they will repel. As with other forces, people use this idea of fields to try to understand how two things can exert a force on each other at a distance. So magnets are no different. We'll picture a magnetic field around a bar magnet as this region of influence. This picture is kind of trying to show that three-dimensional nature of it, although in most notes, in books and when we draw them on paper, we usually just look at kind of one plane and a two-dimensional vector field. You'll see that mostly as we move forward, but keep in mind it really is a three-dimensional field around an object. So when it comes time to visualize the magnetic field around a bar magnet, for example, keep in mind a couple of rules. Number one, outside a magnet, we'll look at situations where you can be inside a magnet, but outside the magnetic field lines point away from the North Pole and towards the South Pole. So you'll see in this picture, that's how they've drawn it. They have these magnetic field lines that kind of show the direction of the magnetic field. Interestingly, if you take a look at this picture down here, they have sprinkled some iron filings around a bar magnet, and you can kind of get a sense of the shape of the magnetic field based on the force that the magnet exerts on these iron filings. They kind of line themselves up in the direction of the magnetic field. We can't see the direction, but you certainly get a sense that there is a lot of iron filings in this region and this region, but there really isn't much here. Which brings us to the second point. When we draw magnetic fields, just like any fields, the closeness or the density of the lines represent the magnitude. So if it's done properly, this is not bad. You kind of get a sense that in this region right here, there's a more dense or more intense magnetic field here versus if we extend this line here, you can see that as we move away and towards the center of this magnet, you kind of get this less dense magnetic field in this region right around here. So being a vector, keep in mind we want to kind of give both magnitude and direction an indication of each of those when we draw magnetic field lines for any particular situation. So we know that magnets can exert forces. We know we can explain these forces using kind of a field theory. But really, what is causing magnetism? If you want to understand that, we have to go back to the experiments of Christian Oersted. Oersted kind of stumbled across the idea that there's a relationship between magnetism and electricity. And he stumbled across this when he noticed that the needle of a compass can be deflected by a current carrying wire. Let me show you what I mean. This is a simulation that kind of shows you what Oersted did in his experiment. Had a current carrying wire. Well, right now it's not carrying a current, but had this wire that kind of went through this region. I'll highlight it right in here, what I've highlighted it in blue. This is the important part. So he has a compass underneath this wire. And right now the wire doesn't have any current through it. And the compass, as you would expect, kind of points north. So if this was Oersted's lab, this would probably be the north, and this would be the south. And as they should do, compasses generally point towards the north of the Earth. When Oersted connected the battery to this wire, he noticed that, as you can see, this needle gets deflected. It's no longer pointing to the north, it's pointing in another direction. If you turn off the current, it goes back to where it should be pointing to the North Pole. If you flip the battery and then connect it, you notice that now the needle is pointing in this direction, kind of towards the top of the page here. Let's flip the battery and we'll see what happens when we leave it on. So when you flip the battery, you can see that the needle points downwards from our perspective, or upwards if we send the current the other way. So notice two things are going on here. Notice what's happening to the current flow that they show here, and notice what happens to the compass. So when the current is in one direction, the compass is in a certain direction, indicates a certain direction of the magnetic field. If we flip the battery, then now the current's going the other way, and the needle's pointing the other way. So this is a big discovery. Really kind of shows a connection between electricity and magnetism, something that really people had been studying totally separate. Electricity was its own phenomenon, magnets were their own phenomenon. Oersted kind of made this connection, or this bridge between electricity and magnetism. Clearly there's a connection. Exactly what it was still had to be investigated. So let's fast forward to the current theory about magnetism and its cause. Really comes down to something referred to as the domain theory. And just to be clear, it's not totally understood, but we have some pretty good ideas about what's happening between electricity and magnetism. So first of all, domain theory proposes that the motion of electrons creates tiny magnetic fields. So just like in Oersted's discovery, he found that it was the moving charge that made the compass needle deflect. It's really this motion of electrons that creates tiny magnetic fields. So this turns out to only happen in certain things that we refer to as ferromagnetic materials, things like iron, should be a comma here, nickel, and cobalt. But it doesn't happen in other materials like aluminum and copper. So why is this? Well, it turns out that if you were to look really closely at those particular metals, iron, nickel, and cobalt, if you picture iron, nickel, and cobalt as having a nucleus, and then surrounding the nucleus you have some negatively charged electrons, these electrons are going around this nucleus in this kind of orbit. Well, Oersted showed that a moving charge or current causes magnetic effects. You can see that the wire with a charge moving it had some sort of magnetic field around it. Well, if we take that one step further, these moving electrons going around this nucleus will also have a magnetic field around them. Now, it turns out that with iron, nickel, and cobalt, they kind of have a series or a number of electrons that happen to move in a similar direction. So because of this, they basically create a really tiny atomic level north and south little electromagnet on each of the atoms. Keep in mind, other materials, if you looked at other even metals like aluminum or copper, turns out that their electrons kind of go around in random orientation, so they never really work together to create an overall magnetic field. But iron, nickel, and cobalt do. Okay, but that still doesn't make a magnet. In order to have an overall magnet like a bar magnet, you can't just have individual electrons moving, or sorry, individual atoms with their magnetic fields going every which way. We have to have enough of these acting together to create what's called a domain. So picture a series of atoms now. Each atom has a north and south. If we have enough of these atoms working together, we'll get a region that kind of has a north and south pole. So in this little animation down here, this is what they're showing. If I highlight one of these domains, what you're really seeing in this blue region here is you can imagine that within here there's a whole bunch of atoms, and those atoms are lined up with their north and their south poles, and a bunch of them add together to give an overall north and south pole to this domain, this one region. So there's one domain. This region over here would be another domain. So this domain, if you consider the difference between these two domains that I've highlighted, in this domain, all the atoms, if this was a piece of iron, all the atoms are kind of lined up and they're working together in this region, and they're working together in this region, but they're side by side to each other. Notice that they don't overall work together. This is why much of the iron that we find in the world really doesn't act as a bar magnet. You'll notice that this domain has magnetic fields pointing this way. This domain has magnetic fields pointing this way. They kind of cancel each other out overall. So that's this third point. In many ferromagnetic materials, these domains are random, pointing in all sorts of directions. They don't act as magnets because they're not really working together. So how do you make a magnet? Well, if you want to make a magnet, you have to create a situation in which all of the domains, notice on this picture down here, all of the domains are now lined up. So need to have a ferromagnetic material. Has to be something with iron, nickel, or cobalt in it. Why? Because the atoms have to have magnetic poles, north and south. Then you have to have a bunch of atoms adding together to create these domains. And then the final step to make a bar magnet would be, we need to line up each of the domains so that we have an overall north and south on our bar magnet. How do you do that? Well, you can put a piece of iron into an existing magnetic field. So if you hold a piece of iron near another magnet itself, eventually you can cause these domains to start to shift and line up. You know, the image I have is the parking lot analogy. So if we have a parking lot and a bunch of cars that are all pointed, that's bad, a bunch of cars that are pointed in random directions. So one car pointed one way, one car pointed the other way, another car pointed the other way. And we tell these cars, okay, everybody get in your vehicle and hit the accelerator. Well, these cars all crash. Nobody ends up going anywhere. It's like a big smash up derby. They're not working together. That would be a ferromagnetic material like a piece of iron that isn't acting as a magnet because of the domains. On the other hand, if we can influence these things and say, hey, listen, everybody point your cars in one direction. So in a magnetic material, that would be like, oh, let's put this randomized piece of iron into a strong magnetic field. And then this piece, I'll draw it the same. Then we can make all these domains line up in one direction. Then when we tell everybody, hit the gas, well, everybody starts to go somewhere. Everyone's working together. So we get this overall magnetic field around this piece of material. All right, I think I'm going to stop there with this lesson. Really two things going on in this lesson. Number one, this idea that we have like magnets that have their north and their south poles. And because of that, they'll have some sort of magnetic field around them. And the magnetic field around a bar magnet, we can picture as this kind of lines that go from the north side to the south side, something like this. In terms of density, the further you get from the poles, the weaker it gets. So they kind of come around. I'm trying not to cross them, just like we learned with electric fields. These lines shouldn't cross. So something like this. All right, pretty bad picture, but in terms of showing the magnitude with the intensity and the direction, so the direction goes this way from north to south, if I want to indicate that. So not the greatest of pictures, but that's the idea. So number one, you draw your field lines from one end of the magnet to the other, indicating the density with the the magnitude with the density of the lines, which is kind of natural when you draw it, and then arrows showing that the magnetic field goes from north to south on the outside of the magnet. I guess inside the magnet, if you wanted to say, well, what is happening if we kind of looked on top of the magnet, then they would go back around. So really, to get a more complete picture, we usually focus our attention outside of a magnet because for a bar magnet, that's our only option, is to be on the outside. And so the magnetic field lines go from north to south. But then you can kind of picture if you could get inside or on top of the magnet, they have to return back. So these magnetic field lines are these concentric circles. They're complete circles. They cycle around here. So that's the first thing, is magnetic field lines. And then the second thing, I guess, is this whole idea of Oersted and his discovery and domain theory. This idea that we go from an atom with its individual little teeny tiny magnetic field with north and south, a group of atoms working together we would refer to as a domain. And then if you get a series of domains working together, you have an overall magnetic material. So that's the domain theory. That's how we kind of understand. And that's really kind of starting to put together this idea that Oersted figured out, that there's some sort of connection between electricity and magnetism. And so we're going to start down this path now, and you'll see that, what used to be two separate fields of study for science really is just one. We don't think of electricity or magnetism. We really think about electromagnetism, and they're really kind of two sides of a similar phenomenon. So like I said, we'll stop there. A lot of conceptual stuff to start. If you have any questions, we'll have a chance to go through it at some point. Post any questions or comments on Google Classroom, but we'll start there, go back, have a look, make sure you have an understanding of these concepts. Next lesson, we'll start getting into some more, interesting. We don't look at bar magnets, to be honest with you. We don't stick with bar magnets a whole bunch in Physics 30. We really want to move on quickly into this idea that Oersted came up with, that, hey, when you have a moving charge in a magnetic field, it will create, a moving charge in a wire, it will create a magnetic field.